In this video, we're going to talk about another technique to combine gates in order to make more complex quantum circuits. When we combine quantum operations in series, we need to do that with a matrix product. Matrix vector multiplication was used to discover what a quantum state would be after it evolves through a quantum operation. So here we have a matrix, an initial vector, and the result vector. Whenever we want to describe a series of quantum operations, we can use matrix-matrix multiplication in order to calculate the overall transfer function that describes that combined operation. Whenever we have a matrix transforming n qubits, the matrix is going to be size 2n by 2n. Let's look at an example of matrix-matrix multiplication. Remember to think row times column. We have two matrices here, matrix 1 and matrix 2 as our operands, and then a resulting matrix. So these are all quantum gates. Here we have row times column to create this first element, row times the second column to create the top second element, bottom row times the first column to create the bottom left element of the result matrix, and then row times second column in order to create the bottom right element of our combined operation matrix. Some notes about matrix-matrix multiplication. Sometimes we can see the operation without an operator between the two matrices. So this means that we are combining matrix A and matrix B with multiplication. It's not a commutative operation, so A times B is not equal to B times A in general. If A is of size n by m and B is of dimension m by k, the resulting matrix will be the outside dimension, so n by k. Because we're always working with square matrices, the resulting matrix will always be the same size as the two input matrices. So that's going to be of size 2 to the n, where n is the number of qubits that operation transforms. Let's build the matrix for a circuit. So here we have a sample circuit, and we use tensor product to combine operations in parallel. So we would have to come up with a matrix for these combined operations and these combined operations. The rules for that are top-down, left-right for tensor product of groups in parallel. So we have group 1 equal to not tensor identity, group 2 equal to not tensor not, and then group 3, we have the swap operation matrix. Matrix product is used to combine all operations in series. So once we have these 2-qubit matrices that describe each part of the circuit, we combine them using matrix product. The rules for matrix product are right, left, left, right, whenever you're combining those operations with a product. So we do right to left, left to right for your multiplication. It might seem like we're multiplying in reverse, but it actually does make sense when you think about it step by step. So think about how the quantum state would be calculated at each point in the matrix. We have the collective qubit state for both qubits of state 0, 1, 2, and 3. If we're to think about the transformation at each point, we would have state 1 formed by state 0 multiplied by overall operation G1. We would have state 2 formed by G2 multiplied by state 1. And if we think about what that actually represents, it's G2, G1, state 0. To determine state 3, we have G3 times state 2, or G3, G2, G1 times our initial state, state 0. Even though it seems like we're doing our multiplication in reverse, going from G3, G2, G1, it's actually how the state progresses through the gates. So let's calculate M. Step 1. We need to have the matrix for each group. So G1, group 1, is going to be formed by not tensor identity. So we have the not operation, tensor product by the identity operation, and we get the following matrix that represents the overall operation on 2 qubits for G1. Now for G2, not tensor not. We have the transfer matrix for not, tensor the transformation matrix for not to get the overall matrix for G2 in our circuit. Group 3 is easy. It's just a swap operation. So we take the matrix for that gate. Now step 2 for calculating n. We're going to multiply for the overall matrix. So m is going to be the combined operation of G3, G2, and G1. So we're going to take swap times not tensor not times not tensor identity, which we calculated in the previous step. So we have our matrix for swap and not tensor not. If we combine those with matrix multiplication, we get the following gate, or we get the following matrix. We pull down our matrix for not tensor identity, and that results in the overall matrix for n being the matrix that represents the circuit as a whole. And that's the combination of group 1 and group 2 and group 3. To summarize, matrix-matrix multiplication is used to combine quantum operations in series. Operations must be of same size in order to do our multiplication, so 2 to the n, where n is the number of qubits transformed. And order matters whenever you're combining gates, and that's for both in parallel and in series.